Okay, so this video is all about alkynes in general, and in particular I've already taught you a fair bit about alkynes already, kind of scattered throughout. Specifically, the way you make alkynes is to take a dibromo species, either vicinal or geminal, this one's vicinal, and expose it to a whole pile of a really strong base, or alternatively a weaker base but a lot of it, and heat. And what it ends up doing is eventually making the alkyne. Now the alkyne itself is notable because the hydrogens at the terminal ends have a pKa of about 25, which means that they are relatively acidic. So you can take a base with a relatively higher pKa, like sodium hydride, which has a pKa of about 35, and deprotonate one of those two hydrogens. And then if you throw in a primary iodide or bromide or chloride or whatever, you can do an SN2 type reaction. And so what this is doing is deprotonating one of the two terminal hydrogens, and then you throw in methyl iodide in the second step, and that installs the methyl group. But of course there are two such hydrogens, so you could do them both sequentially. First hit it once, throw in methyl iodide, then hit it again, throw in ethyl bromide, for example, and that would end up making this particular material there. And again, the key feature is that we're doing SN2 type chemistry for that second step, so I introduced this concept largely right after we had dealt with SN2. Meanwhile, of course, the first step that we talked about here was elimination chemistry, so even though it's how you make the alkynes, I didn't really mention it until it was E2 elimination time. The limitations on alkynes for SN2 type reactions are essentially that you have to do it with primary substrates, otherwise you get some elimination, because this is of course basic once you have deprotonated. So we can do SN2 reactions as long as you have good solvents lined up and you are doing this with primary substrates. But if you meet those two conditions, then you can do sequential SN2 reactions to make straight chain molecules like that. And then we've talked briefly about how you can convert these into other useful products by partially reducing it by, say, throwing in H2 and Lindlar's, so hydrogen gas and Lindlar's catalyst, which is a poison catalyst that will stop halfway. So the hydrogen gas and Lindlar's explicitly will make the cis alkene. You can, however, use sodium and ammonia, sodium metal, which wants to become sodium plus and ammonia, or alternatively, another option would be to use lithium metal, which again wants to become lithium plus, and both of those in the presence of ammonia will do the reduction, partial reduction of the triple bond down to the double bond, but now in transform. In both cases, if you wanted to convert it straight to the alkane, you could just use hydrogen gas and palladium on carbon, and that will convert that down into the alkane itself. Or, of course, this was introduced with the concept of using hydrogen gas and palladium on carbon directly onto the triple bond to take it down to the alkane. So anyway, this is the chemistry you already know, but now that we've started doing addition reactions, you are ready to learn some additional chemistry. Like, for example, if you do the standard deprotonation, and again, the pKa of those hydrogens is about 25, the pKa of sodium hydride is about 35, you can deprotonate and put a minus charge at this position. And if in fact you have a minus charge right at that position, then you should recognize that you can do epoxide opening type reactions. And under SN2-like conditions, you can go ahead and open the epoxide. And the result of this will be to install two carbons and an OH after an acidic workup. So this is now chemistry that you can take advantage of. You can install a bunch of 2-carbon units by first deprotonating and then throwing in oxirane specifically. But of course, this is an SN2-like process that takes advantage of the fact that this material is quite strained. So even though you are limited to using primary substrates in these kinds of reactions, you are not limited to using primary substrates necessarily with the epoxide. Again, what causes this to go is the fact that it's spring-loaded and ready to pop open. So we can take advantage of that. So this is one of the new reactions that would now apply in the context of alkynes. Alright, so now let's imagine throwing in the kind of reagents that we know to do addition reactions with double bonds. Will it work? And the answer is, of course, yes, because the triple bond can serve as a nucleophile just as well as a double bond can. And in the case where you can differentiate the two potential cations from each other, then you will go ahead and prepare specifically this cation, which is going to be an exceptionally high energy cation because a secondary but vinyl cation is bad news. But if you have the chloride floating nearby, then in fact you end up making the product that you'd expect, which is to say chloride bound at that position at the secondary. Now, with, say, this material NHBr, you can't tell which cation is going to be better. They're both going to be secondary and they're both going to be vinyl, and so you end up making both potential products, and there's really no differentiating them. So you'll make some of that, and you'll also make some of this. If you were to go ahead and react this material with an additional additional equivalent of HCl, then of course you would imagine that you could go ahead and perform the indicated step, and naturally you will end up having the chloride wrap around and add to the secondary over the primary, so you end up delivering the chloride to the same exact spot in your second addition. So if you use a single equivalent of HCl, it does this addition and stops there, and it explicitly will react preferentially with the triple bond as opposed to the double bond. So you can in fact stop this reaction here. If you add in a second equivalent of HCl, then it will proceed on to these products as drawn. If, however, you were to subject each of these to an additional equivalent of HBr, you might find something strange, and that is that all of a sudden you can differentiate between the two cations that form. And so, of course, the first step in each case is going to be double bond attacking the HBr, and what that will create in the immediate short term is a pair of cations, potentially, but only one of those cations is going to be the more stable carbocation. And naturally, because of the possibility for resonance, you would prefer to have the carbocation be at the alpha position where the bromide is bound as opposed to the other secondary position. So there is a preference here, and there's going to be a preference for the one that allows you to have some resonance. Likewise, you're specifically going to generate the carbocation that can be stabilized by resonance from the nearby bromide. In both cases, you now have some nearby Br- floating around, which can then go ahead and add in. And so, as you might expect, you end up making the dibromo species in both cases, and that should not be surprising at all. So the moral of the story is that you can start with this material and add HBr and pause in between, and you're going to generate some of each product, ideally 50-50, because there's really no difference between the two products. It's not going to prefer one over the other. However, if you were to add in a second equivalent of HBr, then it will add in such a way as to put both bromines bound to the same carbon. So you're specifically going to make geminal dibromo in both of these cases. So if you add HBr twice, what you end up doing is making this specifically. And so in other words, if you do it sequentially, if you do HBr, it'll make this and then this. If you add HBr a second time, you'll make those. Or you could simply use two equivalents of HBr in the first place, and it will make both products simultaneously, because again, there's no preference, but once you have gone through the first stopping point, then the second one is going to add to the same position. So if you'd like to generate geminal dibromides, what you do is you subject this material to two equivalents of HBr, and that will do what you want. Leaving the mechanisms behind entirely, though, if you were to subject this material to one equivalent of Br2, then what you would form is the vicinal dibromo species that you might expect. And of course, mechanistically, what's going to happen is the triple bond attacks, creating the cation, and the other bromine adds, but it leads to this material as drawn. Of course, using a second equivalent of Br2 will then simply generate the tetrabromo species that you'd expect. And again, it's going to proceed via the mechanism that you'd expect, making first the bromonium and then opening it up. Here, you might expect it to go via some sort of carbocation or bromonium. Presumably, it will go through a bromonium, although you can't be entirely sure because that might end up being a bit strained. So anyway, the idea is that if you take this material and you add in Br2, what you will do is form the vicinal dibromo species via the mechanism you'd expect, where the double bond goes ahead and adds to one of the two Brs while the Br adds back, creating the bromonium species. The other bromine wraps around and opens it as expected, leading to the trans material specifically. Meanwhile, if you then add in a second equivalent of Br2, what that ends up doing is making the expected tetrabromo species as drawn. You might wonder what happens if you add water to the triple bond, and here's where things take a turn for the slightly bizarre. So if we were to add, say, mercury in the presence of some acid, what ends up happening, as long as you have a substrate where you can differentiate the carbocations that would result, you end up making this ketone instead of what you might expect. And this will take advantage of ketoenol tautomerization, a mechanism that you should definitely watch the video for and really internalize how this works. But I'll walk through the actual mechanism for how this happens in a separate video. However, you can also take the exact same material and add water in an anti-Markovnikov sense. So of course, this was the result of a Markovnikov addition. And here, of course, you would use Borane to do the anti-Markovnikov addition, followed by the usual oxidative workup, which is to say hydrogen peroxide, sodium hydroxide, water, and so on. And what it will do is form the aldehyde. And again, 1, 2, 3, 4 carbons, so 4 carbons here, except now it makes the aldehyde instead of the ketone. And this, of course, would be a anti-Markovnikov product. Again, the way this is going to work will involve similar steps at the beginning to what you'd expect, and then it will take a turn for the bizarre once the enol that you form form rearranges to the other tautomer. And in the case of the possibility of making an aldehyde, a ketoenol tautomerization actually leads to an aldehyde instead of a ketone. Although I should note here that the way that this is organized in order to lead to the anti-Markovnikov products is in terms of size, and so you could use BH3 at this position, or alternatively you could use something like 9BBN, which you could just simply write as 9BBN, or alternatively I've drawn this out for you as abbreviated this way, or alternatively there's the Borane reagent that Prof. Miller suggests, which is the dicyamal borane, which can be abbreviated either that way or as dicyamal borane. Any of those three reagents are likely to be much more selective than the borane I suggested first, but they will lead to the same fundamental products. Using boron to add water across a triple bond in an anti-Markovnikov fashion will lead to an aldehyde. So the main reason to bring these two possibilities up is because it's going to be one of the very few ways that you have to make ketones in the course or aldehydes in the course. If you see a ketone, that came from a Markovnikov addition to a triple bond or alternatively ozonolysis. And likewise, if you see an aldehyde, well, that's coming from a borane addition to a terminal alkyne or alternatively ozonolysis. So again, not a whole lot of tools that you have, so if you see a handle like this, handle meaning a synthetic functional group, then what that means is you probably have a pretty good idea of how it was made, either via addition of water to triple bonds or alternatively ozonolysis.